Okay, we're going to take a look at number 8 in section 7.7. Going to determine whether this improper integral here converges, and if so, we're going to evaluate it. If it diverges, we're going to, according to the instructions, put infinity in, the symbol for infinity, to show it that it diverges. All right, this function here does not have an infinite limit of integration, but it does have a vertical asymptote. I hope you can identify the fact that when x is 8, the denominator being 0, we're going to have a vertical asymptote. I actually graphed this just for fun. This function, 1 divided by the square root of 64 minus x squared. On the interval, this is on the interval from 0 to 8. The y scale is from 0 to 1. Notice when I plug in 0 into the function, I'll get this 1 over the square root of 64, 1/8. So the height of the function is 1/8. And it seems like it stays pretty close to 1/8, but then all of a sudden, right, as we start getting close, by the time we get to 7, we start moving up. In fact, very rapidly we shoot up. This is a vertical asymptote there, right? So I want to see, can we integrate? Is the area under this curve from 0 to 8, is it finite? And the answer is actually yes. And the answer is kind of interesting for what that area is actually going to be. So when we look at this, I just want you to recall we're going to have to integrate this function 1 over the square root of 64 minus x squared. A regular u substitution will not work. You can either recognize the fact that hopefully you remember this as the antiderivative of the arc sine or inverse sine function, right? Uh, or the antiderivative of this rather is the arc sine or inverse sine function. So it's not quite the same thing because of that 64. So all you have to do to get it to look like this is factor out a 64, right? Under that radical, you're left with 1 minus x squared over 64 or 1 minus x over 8 squared. I can then break up this uh, product as the product of 60 square root of 64, which is 8, and the square root of this. Now, if I let u be x over 8 or 1/8 x, I get du is 1/8 dx, so 8 du is dx. So pulling out the 1 over the square root of 64, the 1/8, the dx is the 8 du, and this becomes square root of 1 minus u squared. Notice the 8 times the 1/8 just becomes 1, and we get this. Well, guess what that is? It's just this with u instead of x. So we get sine inverse u, but remember what u was. It was 1/8 x, or x divided by 8. So end story, antiderivative of this function is going to be the arc sine of x over 8. So now we'll do the definite integral. Now that we've got the antiderivative, what is the definite integral from 0 to 8? Well, it's an improper integral. Oh, by the way, you could have also used trig substitution to find this antiderivative if you let x be 8 sine of theta. If you thought to do that, it works out very nicely as well. So you could have done that as well. Sorry. Okay, back to this. The integral from 0 to 8 of this is going to be the limit, remember, of t as it approaches 8 from the negative side, right? So we're approaching from the negative side as we're getting closer and closer to x equal 8 from below. This is where we're approaching. So what's the antiderivative? Well, we found that. That's inverse sine of x over 8. I plug in t and then plug in 0. Of course, 0 divided by 8 is 0. 0 divided by 8 is 0. The arc sine of 0 is 0. And I've got now, what's this approaching then, since that goes to 0? What's this thing approaching as t approaches 8? Well, it's getting closer and closer to what? 8 over 8. Sine inverse of 8 over 8, or sine inverse of 1. That's what it's approaching, sine inverse of 1. Well, arc sine of 1 is pi over 2, since sine of pi over 2 is 1. And that is the value of this definite integral. Of course, the integral converges, but that area that we showed you a minute ago, the area under this curve, which has an infinite perimeter, but a finite area, is equal to exactly pi over 2. Kind of interesting, about 1.57, but very neat little problem. Okay, hope this helps.